Let's play around with support vector machines. Open up the SVC notebook in your course materials. And fortunately, it's a lot easier to use support vector machines than to understand how they work. So for this example, let's go back to the same clustering sample data that we created for our k-means clustering lecture. We just have this create cluster data function here again. We're going to put in a consistent random seed, so you'll see the same results that I see here. We will pass in a given number of clusters that we want, and a number of points per cluster will be computed by n over k. So basically we're passing in how many clusters we want and how many total points we want to distribute between them here. We then create our x and y arrays here. X will contain our feature data, which will be 2D points consisting of incomes and ages that are randomly generated and fabricated, and y, our labels, will represent the clusters that these points are associated with. So for each cluster we want to create, we'll pick a random income centroid and a random age centroid randomly selected between 20 and 70 years and $20,000 and $200,000. And then for every point per that cluster, we will create a fictitious point randomly sampled with a normal distribution for a given income and age around those centroids. Those will be appended to our X feature array, and then we'll append the actual cluster number to our Y label array. We'll convert those back to NumPy arrays and return them back. All right, so now we'll actually prepare our data here. So we'll actually call create cluster data. We're going to ask for 100 points broken up into 5 different clusters, and that function will do that for us. And let's plot what it comes back with. So we'll just say we want to create an 8x6 plot here, a figure, and we will do a scatter plot with the color being correlated with the actual label associated with it. That will make sure that each cluster gets its own color. We'll then plot that. Now, it turns out that in order for SVC to work well in some kernels, especially the poly kernel, we need to scale that data down to a normally distributed range between -1 and 1. Otherwise, the solutions might never converge. So we're also going to scale this data down to the range -1 to 1 here. And to do that, we're using something called min-max scaler that comes out of the pre-processing module of scikit-learn. And we'll just say we want to fit all the features in the X array, which contains all the incomes and ages, to the range -1 to 1. We'll apply that transform to our feature data, and then we'll plot the resulting scale data as well. Now, if you ever wanted to get back to the original data range, there's also an inverse transform function on min-max scaler you can use to go back the other direction. But for this example, we won't need to do that. Anyway, let's go ahead and run these before we forget. So I'll go back up to the function definition block here and run that, Shift-Enter. And then in block 2, Shift-Enter again. And you can see here the plot of our unscaled results, where the incomes range from 20,000 to 200,000, plus or minus some slop value there. And our ranges are roughly 30 to 70 years old for the age axis. So basically, our feature data consists of incomes on the x-axis and ages on the y-axis here. After we scale it, it looks exactly the same, except the actual numbers have been scaled down to the range -1 to 1 on both axes. So that's prepared our data for being friendly to SVC. Now we just have to actually apply SVC, which is incredibly easy. All we have to do is import the SVM package from scikit-learn and call svm.svc. Specify the kernel that you want. We'll start with a simple linear kernel. The main hyperparameter that matters here is C, which is by default 1.0. That works well. And we'll ask it to fit to our feature array and our labeled array. So basically we're saying fit with our array of all the 2D points of ages and incomes and all of our labels of what clusters we know those are assigned to originally. So that will train our SVC model. Let's go ahead and run that. Went really quickly. So let's take a look at the results. What we're going to do here is create a plot where we can actually visualize the ranges within this 2D space of ages and incomes that our model thinks correlates to given clusters. And at the same time, we'll plot the actual results of what clusters it thinks each individual point is in as well. So to build up this graphic, we first need to build up a very dense 2D array that we can actually create predictions on, so we can actually plot what those clusters are at every point in this space. To do that, we're calling mesh grid on NumPy, saying that we want a grid of sample points here that range between -1 and 1 in both the x and y axis at a spacing of just 0.001 apart from each other. So this is close enough that it's going to look like a continuous range of color when we actually plot this. We then need to convert the result from mesh grid to NumPy arrays so we can use them with a classification prediction. And then we need to convert that in turn to a list of 2D income age points. So the ravel function here is just converting this back to NumPy arrays. And the np.c underscore, c underscore is shorthand for concatenate. That says I'm going to take all of these x values and all of these y values and concatenate them together into a list of points that have xy, 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 etc. So now that I have that list of sample points, I can pass that into predict. Now, just to clarify a point of confusion here, x and y here correspond to the x and y axes. So NPX is going to end up being all of the income data, and NPY will be all of the age data. All right, so don't let that confuse you. When we talk about y in this context, I'm talking about the y-axis, not the label data y. So we have this feature array we're going to pass into predict, and that will give us back predicted labels, which are the actual cluster numbers for each point within this space. Then we just have to plot it out. Again, we'll make an 8x6 figure. We will reshape those results to make sure it matches the x dimension of our plot. And then we'll call contour f. This will basically go through every single point that we created on that mesh grid and take its labels that were predicted. So these are the predicted labels, not the actual labels, and plot them using whatever color map we want to use associated with those values. And after that, we'll actually do a scatter plot that is going to plot the original points that are still living in our capital X array there, our feature data. Again, that's income and age. And we will color them based on the actual original clusters, calling y as type float to convert those original labels back to color values for the plot. So let's go ahead and run that and see what it looks like. Takes a little bit of a while to create that many predictions, but not too long. And you can see here what happened. So remember, what we're doing here is plotting the actual ranges of predictions as this background color. So we're using a linear kernel, so we have straight lines delineating each region where it believes these clusters correspond to. So basically anything in this triangle is going to be modeled to be in one cluster. Anything that's on a red background will be another cluster. And we're plotting on top of that the original true clusters from when we actually created the data. Now, these clusters do overlap to some extent, so it's not going to be possible or realistic to really expect any algorithm to be able to get 100% on this. You can see that it missed a couple. So for example, we have this blue feature here that's showing up as a different color than the rest of the ones that should be in the same cluster here. The background colors don't necessarily correlate with the foreground, but you can see when a point doesn't match its neighbors around it for the rest of that cluster, that's probably going to be an incorrect result. Also, we have this purple point here for this cluster that seemed to have snuck into this red region here that really belongs to this other cluster here. So a couple of points it got wrong, but can't really fault it too much for that. The clusters do in fact overlap. Now you can also use the predict function on the trained model to make predictions for specific new points that the model hasn't seen before. That's kind of the whole point of all of this. So in this particular example, we're calling svc.predict to predict a cluster for someone with an income of $200,000 at age 40. And it turns out that lands in cluster number 3 with our model. And for someone with $50,000 at age 65, that ended up in cluster number 2. Now note that we have to scale those numbers down first before we can actually make a prediction using them. So remember that before we trained this model, we scaled all of our inputs down using min-max scaler. So we have to use that same scaler, which we named scaling, and use that to transform our input data when we're trying to make predictions for new individual points as well. So very important not to forget that step. It's very easy to do, and I've done it myself. But with that, I will challenge you to extend this, and for your activity here, try different kernels. So linear is just one of them. Go and look up the documentation in scikit-learn online for the SVC model, which itself is a good exercise because you can answer a lot of your own questions that way, and find out what the other possible kernel options are. See if you can find a better one. When you get into nonlinear kernels, maybe those can fit this data a little bit better actually and do a better job on it. So just do some experimentation, try different kernels, see what effect that has on the shapes of the clusters and the regions that define them. You might find it interesting. And also see what effect it has on the runtime. Some of these are more complicated than others, and some of them require more computational resources than others. So that's also a trade-off you have to consciously make too. Also, you might want to fiddle around with some of the hyperparameters associated with these different models. They'll be documented in the documentation in scikit-learn for each kernel type. Many of them have very many different parameters, and you just have to experiment to find the parameters that work best. So play with that as well. Hyperparameter tuning, very important part of machine learning. So go and get your hands dirty, if you will, and see if you can do a better job using a different kernel type.